People ask me this question constantly: is the universe infinite? And the honest answer is that it depends on something we still do not fully understand. It depends on how much matter actually exists in the universe, and how strong gravity truly is on the largest possible scales. Those numbers decide everything. But even with what we know today, the mathematics already points to outcomes that are far stranger than most people ever imagine. Right now, space itself is expanding. This is not a metaphor, and it is not an illusion. Galaxies billions of light years away are moving away from us at enormous speeds, sometimes thousands of miles per second. The strange part is that the farther away a galaxy is, the faster it appears to be receding. This is not because those galaxies are actively traveling through space like rockets. It is because the space between us and them is stretching. The universe is growing larger every second. You cannot feel this expansion. On human scales, the effect is incredibly small. Your body is not expanding. The Earth is not expanding. The solar system is not expanding in any measurable way. Gravity holds local structures together, but on cosmic scales, over millions and billions of light years, the expansion is very real and very measurable. And once you accept that space is expanding now, a powerful conclusion follows naturally. If space is expanding today, then in the past, it must have been smaller. Run time backward and the distances between galaxies shrink. They move closer together. Matter becomes denser. Temperatures rise. Go back far enough and everything we see today, every galaxy, every star, every atom was once compressed into a single, unimaginably dense and hot state. That moment is what we call the Big Bang. The Big Bang was not an explosion that happened at one point in space. It was the expansion of space itself. There was no empty space waiting for matter to fly into. Space and time themselves came into existence at that moment. Everything began together. This idea did not come from philosophy or speculation. It came from observation. In the 1920s, astronomers began studying the light from distant galaxies. When they measured that light carefully, they noticed something unusual. The light was shifted toward the red end of the spectrum. It was redshifted. At first glance, that might not seem important. Light changes color all the time. But this redshift followed a precise pattern. The farther away a galaxy was, the greater the redshift of its light. There is only one explanation that fits this pattern. When an object moves away from you, its light is stretched. The wavelength increases. The color shifts toward red. It is the same effect you hear when a car passes by, and the pitch of its engine drops as it moves away. Light behaves the same way. The redshift showed that galaxies are moving away from us, and the relationship between distance and speed showed that space itself is expanding. So the universe began in a hot, dense state and has been expanding ever since. But that immediately raises the next question. What happens in the future? Does the expansion continue forever, or does it eventually stop and reverse? The answer depends on gravity. Everything in the universe has mass, and mass creates gravity. Gravity pulls matter together. Even as space expands, gravity is constantly working against that expansion, trying to slow it down. A simple analogy helps clarify this. Imagine throwing a ball upward. Gravity pulls it back toward the ground. If you throw it slowly, gravity wins and the ball falls back. If you throw it fast enough to reach escape velocity, it barely escapes and never returns. Throw even faster, and it flies away easily. The universe behaves in a similar way. The expansion is like the initial throw, and gravity is like the pull back. The balance between these two effects determines the fate of the universe. From this balance, three possible futures emerge. In the first scenario, the expansion is too strong. Gravity is not powerful enough to slow it down significantly. The universe expands forever. Galaxies move farther and farther apart until light from one galaxy can never reach another. Each galaxy becomes isolated, surrounded by darkness. Over time, stars burn out. Energy spreads thin. Everything cools. The universe does not end in a dramatic explosion. It fades slowly into a cold, dark, empty state where nothing interesting can ever happen again. This outcome is often called heat death in the second scenario. The expansion is exactly balanced. Gravity slows the expansion, but never fully stops it. The universe continues to expand forever, but more and more slowly. The expansion rate approaches zero as time goes to infinity. This is known as a flat universe. Its ultimate fate is similar to the first case, endless expansion, but perfectly balanced at the critical boundary between collapse and runaway expansion. The third scenario is the most dramatic. In this case, gravity is strong enough to overcome the expansion. Over time, the expansion slows, stops, and reverses. Galaxies stop moving apart and begin moving toward each other. Space itself contracts. The universe grows hotter and denser. Galaxies collide. Stars are torn apart. Matter compresses until atoms can no longer exist. Eventually, everything collapses back into a single point. This is called the Big Crunch, the reverse of the Big Bang. Which of these futures describe? Our universe depends on how much matter exists, including matter we cannot see directly. In the mid-20th century, this question was still unanswered. But thinking about the universe as a whole led me to consider something smaller, individual. Stars. Stars are remarkably stable for millions or even billions of years. The energy produced by nuclear fusion in their cores pushes outward, balancing the inward pull of gravity. But stars do not last forever. Eventually, they run out of fuel. When fusion slows and stops, gravity takes over. For stars like our sun, this process is relatively gentle. The star sheds its outer layers and leaves behind a white dwarf, a dense, Earth-sized remnant made of compressed matter. It begins hot and slowly cools over trillions of years. But for massive stars, the story is far more violent. When fusion stops in a massive star, gravity overwhelms all resistance. The core collapses catastrophically in seconds. Electrons are forced into protons, forming neutrons. The result is a neutron star, a city-sized object with the mass of the sun. Its density is so extreme that a teaspoon of its matter would weigh as much as a mountain. Even neutron stars have limits if the mass exceeds a critical threshold. Neutron pressure can no longer hold gravity back. When that happens, collapse continues without any known force to stop it. This is where the mathematics of gravity becomes truly strange. Einstein's equations of general relativity describe how space and time behave near massive objects. For planets, stars, and even neutron stars, the equations work perfectly. But beyond a certain density, the equations predict something extraordinary. They predict a critical boundary, a size below which space and time behave in a completely unfamiliar way. This boundary is called the Schwarzschild radius, named after the physicist who discovered it in 1916. For the Sun, this radius is about 3 kilometers. For Earth, it is about the size of a marble. Any object compressed below its Schwarzschild radius becomes something radically different. In the mid-1960s, we called these objects collapsed stars. Others called them frozen stars or black stars because no light can escape from them. The predictions surrounding them were deeply unsettling, especially when considering what would happen to someone falling into one. Imagine a massive star collapsing under its own gravity. Now imagine an observer standing on the surface, falling inward with the star. From far away, watching through a telescope, you would initially see nothing unusual. The star shrinks. The observer falls inward. Light from the surface reaches you normally, but as the star approaches its Schwarzschild radius, something strange happens. The light becomes redder and dimmer. Gravity stretches the light as it climbs out of the intense gravitational field. Time itself appears to slow. The observer's movements look slower and slower from your perspective. As the boundary is approached, the effect becomes extreme. Eventually, the observer appears to freeze completely at the edge. His image is stuck there forever, never quite crossing. His light fades into invisibility. From your perspective, time has stopped for him, and yet, from his own perspective, nothing unusual happens at all. He crosses the boundary smoothly, without warning, without feeling anything special. Only afterward does he realize the truth. There is no way out. All paths lead inward. Communication becomes impossible. Escape is impossible. He is trapped, falling inevitably toward the center. Both perspectives are correct. Time flows differently depending on where you are.
The honest answer is
near strong gravity,
time
slows relative to distant
not little
observers.
hard pieces
This is
of matter.
not science fiction.
In the nucleus,
it is measured fact.
Protons
Time
and neutrons
on
are held together by residual strong interactions, often described as exchange effects involving particles like pions.
Experiments have proven that time flows at different rates. In different gravitational fields, near collapsed
step back
stars.
and ask again,
This effect
what's
becomes
inside
extreme,
an atom? Not
and
planets,
this realization
not
forces
orbits,
us
not
to
balls,
confront something uncomfortable.
not stuff in the
Physics
comforting
predicts
tactile sense.
Realities.
What's inside
that
an atom
defy
is field,
everyday
quantum
intuition.
field. The
Space expands. Time
Citron
bends.
field, the quark
Stars
field,
collapse into
the gluon
darkness.
field,
The universe
electromagnetic
itself may
field.
expand
These
forever
fields
or
fill
collapse
space.
back
They are
into fire.
everywhere, all the time.
Equations
When we
do
say
not
an electron
care
is in the
whether
atom,
these ideas
what we
make
really mean
us
is that the
uneasy.
electron field
They
has an
simply describe
excitation
what is
bound near the
these
nucleus,
differences in time
shaped by the
are
allowed
not theoretical
quantum state.
tricks or mathematical
The atom is not a
curiosities.
thing
They
the way a
are
rock is a
measurable
thing.
facts.
It is a
In
stable
1960,
configuration of
physicists
interacting
performed
field
an elegant and
excitations
decisive
held together by
experiment known
forces
as the
that are
Nussbauer
themselves
experiment.
mediated
A
by
single
other
photon was
excitations.
dropped from the top
There
of
are
a
no
tower
solid
to the
objects
bottom,
at the bottom.
a distance of
There
just
is no
24
final
meters.
stop.
When it arrived,
There are
its
patterns,
frequency had changed.
equations,
The shift was
symmetries,
tiny one
conservation
part
laws.
in 1,000
and somehow
trillion, but it
those
was real
produce
and measurable.
everything you
The
experience
photon
as
had
physical
fallen
reality.
into a region where
And
time
that should
runs
bother
slightly
you,
slower.
because
That
your mind
experiment
wants something
confirmed
solid at the
extraordinary.
foundation. Something
Time
you can
itself
point to and
flows
say,
at different
that
rates.
is what it's made
As
of.
depending on
When you chase
gravity
the atom down
near
to its
extreme
core, you don't
objects,
find
the
solid
effect
pieces.
becomes
You find
overwhelming.
math,
On the
fields
surface of a
defined over
neutron
space and
star, time may
assigning
run
values
at
everywhere,
half the rate
evolving
it does
according to
far away.
differential
1 hour that
equations.
would correspond
Schwartz numbers
to
that
2
sometimes
hours
behave like localized
for a
particles when you
distant
measure them in
observer.
light.
Near the
Spread out
Schwarzschild
wave
radius
functions
of
when
a
you don't.
collapsed
You've
star,
heard the atom is mostly
the
empty
difference
space.
becomes infinite.
But even
From
that
the
is
outside,
misleading,
time
because
appears
empty
to
does
stop
not mean
completely.
nothing.
An hour for the falling
The vacuum
observer
is
could
alive with
correspond
quantum
to
activity.
billions of years
Fields
for
still
someone
exist
watching
there,
from
virtual
afar.
fluctuations
This
still
explains
occur,
why the falling
and the electron's
observer
wave
appears
function
frozen.
extends through the atomic
He is
region
not
as a
frozen from his
non-zero
own point of
amplitude.
view. His
When
heart
you
beats normally.
Push
His
on a
thoughts
table.
flow
You
normally.
aren't feeling tiny
But
billiard
time for
balls
him is so
smashing into each
distorted
other.
relative to
You are
the
feeling
outside
electromagnetic
universe that his
repulsion
motion is
between
stretched
electron
across
configurations
configurations. Even Earth
and the exclusion
demonstrates
principle
this
preventing
effect.
identical
Earth's core
electrons
is
from
younger than its
occupying the same
surface
state.
by about 2 days.
feels
Over
solid
4
because the
billion
rules are
years.
strict,
Gravity
not
has
because matter
slowed
is made of
time
little
deep
hard pellets.
inside. The
Scale
planet
makes
just
it
enough to
worse.
produce that
The
difference.
nucleus
This
is
is
about
not
100,000 times smaller than
It is
the atom.
measurement. It is as
If the
real
nucleus
as any
were the
fact
size
in
of a
physics.
marble, the
So
atom
if
would be the
collapsed
size of a
stars
stadium.
truly exist,
Yet the electron,
how
as far
could
as
we
can
ever
tell,
find
has
them?
no
By
size at all.
definition, no light
Experiment
can
after
escape from within the
experiment is
Schwarzschild
consistent
radius.
with it being
They
pointing.
are invisible. They are dark
point-like
holes in
entity
space where
occupying
stars once shine.
a vast
But
atomic
invisibility
region
does
through
not mean
probability.
undetectable.
Does that
One
make
method
intuitive sense?
involves
Of course
binary
not.
star
Nature doesn't
systems.
care.
Most
Then there's
stars
spin.
are not solitary.
Electrons
They
have
orbit a
intrinsic
companion.
angular momentum, yet they
If
cannot
one
be
star
literally
in such
spinning
a
like a
system
top because
collapses
the point
into
has
a
no
dark
extent to
object,
rotate.
the
Still, the
star
property
will
exists,
continue orbiting, but
quantized,
now
so you
it will
only
be
ever
orbiting.
measure discrete
Something
outcomes.
unseen. By carefully
Energy
tracking
levels
the
are
motion of
quantized
the
too.
visible star,
The electron can only have
astronomers can
specific energies
calculate the
because the
mass
wave
of its
function must
invisible
fit
partner.
into allowed
If that
standing wave
mass
patterns around
is
the nucleus,
too large to
like
be a neutron
harmonics on a string.
star, and no light
When
is
it changes
emitted,
levels,
the only
it
remaining
emits or absorbs a
explanation is
photon
a
with
collapsed
exactly
star.
the energy difference,
This method is
producing
powerful
precise spectral
because it
lines.
relies
We
purely
can calculate
on
those
gravity.
lines to absurd precision
Gravity
and
cannot hide.
experiments
If
match
something
them.
has mass,
The theory
it leaves
works,
a signature.
but your intuition
And many
never
binary
gets a neat
systems
picture.
exist. If
And
collapsed
when you try to
stars
look
are
inside
real,
the atom,
some
you
of them
run
must
into another
reveal
fundamental
themselves
wall.
this way.
To resolve
Another
small
possible
scales, you
method
need short wavelengths,
involves
which means high
gravitational
energy,
lensing,
which means you
according to
disturb the
general
system.
relativity.
There
Mass
is no
bends
passive
space,
observation in
and
the
bends
quantum
space
world.
bends the
Measurement
path of light.
doesn't
This
merely
effect
reveal
was
a
first
pre-existing
confirmed
fact.
in
It
1919
forces a
when
definite
starlight
outcome from a
passing near
range
the
of
sun
possibilities.
was observed to curve during
Before
a
measurement,
solar eclipse.
a wave
A
function,
collapsed star would
a
bend light
superposition
far
of
more dramatically.
potentialities.
If a
After
distant
measurement,
star
one actual
passes
result.
directly behind a collapsed
So
star
what's
from
really
a perspective,
inside an atom?
its light could be
Not
distorted,
little balls,
split,
not orbits,
or
not
even
mechanical
form a ring.
trajectories.
The alignment
What's
required
inside
for
is
this
a mathematical
is extremely
structure,
precise.
a wave function
The odds
governed
are
by the
small,
Schrödinger
but the
equation
universe is
built
large,
from quantum
and
fields
improbable
whose
events do occur. With
excitation
enough
not
sometimes look like particles. Such an effect could be seen. You can't truly in the mid-1960s
because the wave function
many
isn't
physicists
a physical
were
wave
deeply
in space.
uncomfortable
It's
with these conclusions.
Some proposed that stars
simply
space,
could not collapse
encoding
beyond the
complex
Schwarzschild
probability
radius
amplitudes.
They argued that something must prevent it. Perhaps the star would explode in a supernova, shedding mass to avoid total collapse.
That is what's inside an atom.
But this argument explains nothing. It merely assumes the outcome it wants to avoid. Others adopted a more dismissive attitude. They argued that since we cannot see inside, the Schwarzschild radius and the mathematics breaks down at the singularity, the problem is not worth worrying about. As long as observers remain safely outside, they claimed, physics does not need to describe what happens inside. This attitude is deeply unsatisfying. The observer falling inward has a real experience, a real fate. Ignoring that fate because it is hidden from view is not science. It is avoidance. Physics does not get to choose which questions are comfortable. If the equations predict something strange, then the task is to understand it, not dismiss it. Running away from difficult conclusions does not make them disappear. Consider what is happening right now in the universe. Somewhere, a massive star is exhausting its fuel. Gravity is crushing it inward. If its mass exceeds the critical limit, nothing will stop the collapse. It will pass the Schwarzschild radius. From far away, it will appear frozen, halted at the boundary forever. Time, from that perspective, has stopped, but for an observer falling with the star, nothing special occurs at the boundary. No shock, no warning, no physical marker. He crosses in seconds or minutes of his own time. Only afterward does he discover that escape is impossible. Space itself has curved so completely that every direction leads inward. Both descriptions are true. They are not contradictions. They are consequences of the way time behaves in strong gravitational fields. Time is not absolute. It does not flow the same everywhere. It stretches and bends. This realization extends far beyond collapsed stars. Space itself is expanding right now. Galaxies are racing apart. We measure this expansion through redshift. Run time backward, and everything collapses into the Big Bang. Run time forward, and the universe may expand forever or collapse back into fire. We do not yet know which fate awaits us. Individual stars collapse. Entire universes may collapse, or they may drift endlessly into darkness. The mathematics predicts all of these possibilities, and the mathematics is remarkably consistent. Some people are tempted to avoid these ideas. They prefer to believe that stars must always explode before collapsing too far, or that we should not worry about regions we cannot observe. But that is not physics. That is fear disguised as caution. The universe does not care about our comfort. It does not simplify itself to match our intuition. It follows rules. And those rules sometimes lead to outcomes that feel deeply unsettling. The observer falling into a collapsed star has a real future. Time truly does stop from one perspective while continuing from another. These statements are not philosophical paradoxes. They are physical realities confirmed by experiment. Time flows, but not uniformly. Space expands, but not locally. Gravity bends both. When you take the equations seriously, when you fall, owe them to their conclusions, you discover that reality is far stranger than appearances suggest. The universe is not simpler than we thought. It is deeper, more subtle, more unsettling, and more fascinating. We are only beginning to understand what the equations are telling us. And when we truly listen to them, when we stop trying to force reality into comfortable shapes, we find that the universe is not just vast, it is profoundly strange in ways that challenge the very meaning of time, space, and existence itself. And when you truly let these ideas sink in, something subtle but profound begins to happen. You stop thinking of time as a simple river flowing forward. You stop imagining space as a static stage where events play out. Instead, you begin to see the universe as a dynamic structure where space stretches, time bends, and gravity ties them together in ways that defy everyday experience. This is where most people quietly step back, not because the ideas are false, but because they are uncomfortable. Our brains evolved to deal with falling objects, burning fires, and changing seasons, not collapsing stars and frozen time. Yet the equations do not ask for permission. They describe reality, whether we like the picture or not. When a massive star collapses into darkness, it does not simply disappear. It leaves behind a permanent distortion in space-time. Even long after the light has faded, the geometry remains. Space remembers. Gravity remembers. The universe keeps the rico, RD, and that realization leads to an even deeper question. If time slows near strong gravity and effectively stops at the Schwarzschild radius from an outside perspective, what does that mean for causality itself? What does it mean for the idea of before and after? We tend to think of time as universal. 1 second here equals 1 second everywhere. But that is not how reality works. Near a collapsed star, the notion of a shared present breaks down completely. Events that occur for one observer may never fully occur for another. The universe does not provide a single clock that everyone agrees on. This is not philosophical speculation. It is a direct consequence of general relativity. Space and time are woven together, and gravity stretches that fabric unevenly. In extreme environments, the stretching becomes so severe that common sense simply fails. Consider again the observer falling inward. From the outside, his fall never completes. He approaches the boundary endlessly. From his own perspective, the crossing happens quickly. Both descriptions are mathematically correct. Neither is privileged. Reality allows both. This duality forces us to rethink what we mean by existence. Does something exist if it can never be observed completing its journey? Does it exist differently for different observers? Physics gives an unsettling answer. Existence itself can be observer-dependent, and if that is true for collapsed stars, it may be true on cosmic scales as well. The universe itself may have horizons, regions so distant that their light will never reach us, no matter how long we wait. Those regions still exist, but they are causally disconnected from our future. They are effectively separate universes, not by walls or barriers, but by the structure of space-time itself. Expansion creates isolation. Gravity creates collapse. Both shape the ultimate destiny of everything that exists. This brings us back to the original question: is the universe infinite? The answer may not be a simple yes or no. The universe could be